Watch this video in Lesson Reach. Pause and ask questions, take a quiz, or get help with assignments. Link below.
Imagine waking up tomorrow and the numbers 8 and 9 have simply been erased from existence.
Oh, wow.
Right? I mean, how would you count?
Yeah.
How would you even multiply?
Yeah.
Today, we are stripping away the familiar comfort of our everyday base 10 counting system to figure out the true mechanics of how math actually works.
Yeah, and our guide for this mental workout is section 4.5 of chapter 4 from Contemporary Mathematics. For this deep dive, I am basically putting on my lecturer hat, to walk you through the underlying logic of different number bases.
Right, which means I will be the student today, getting my notebook ready and trying to unlearn basically everything I know about basic arithmetic.
Good luck with that.
Thanks. So, okay, let's unpack this. Where do we even begin if we can't rely on our trusty base 10 times tables?
Well, to learn to multiply in a new base, you first have to remember what multiplication actually is at its core. I mean, it is merely repeated addition.
Right, you just add the same thing over and over.
Yeah, exactly. And the foundational rules, they don't change regardless of what base you are in. So 0 multiplied by anything is still 0.
Oh, thank goodness.
Right. And 1 multiplied by anything is still that same number. The identity properties stick around.
Okay, that is a relief.
Right.
But say I want to multiply in base 6. I assume I have to rely entirely on base 6 addition rules. Like, how do I actually calculate something simple, say 2 times 3 in base 6?
So you break it down purely as 2 plus 2 plus 2. We take the first part, right? 2 plus 2 is 4.
Yeah, which works fine in both base 10 and base 6.
Right, but then we add that final 2. In base 10, 4 plus 2 gives us 6. But base 6 only has the digits 0 through 5.
Right, so my instinct is to just write down a 6, but that number literally doesn't exist in this system. It's just gone.
Exactly. And this is where you have to completely rethink place value. Because in base 6, a 1 and a 0 doesn't mean 10.
Oh, right, because it's not base 10.
Yes, it means you have exactly one group of 6 and 0 ones left over. Since 4 plus 2 gives you exactly 6, it rolls over into one group of 6.
Ah, so it's written as 1, 0.
Correct. Therefore, 2 times 3 in base 6 is 1, 0. And what's fascinating here is that to create an entire multiplication table for a brand new base, you don't actually need to memorize anything new.
Wait, really? Nothing at all?
Nothing. You only need to perform this repeated addition process once for each entry.
Okay, I see how addition builds the multiplication table, but, division usually hurts my head even in base 10. How on earth do we tackle division without a calculator?
Well, the process of division in other bases is completely identical to base 10. Think about our normal math.
Okay.
72 divided by 9 is 8, simply because 9 times 8 is 72. You just apply that exact same logic in a new base.
So you just look for the corresponding rule in the new multiplication table you just built.
Exactly. It is literally just reading the table in reverse.
Okay, if division is just reading this alien table backward, my brain is already hurting. But here's where it gets really interesting. What are the common errors people make in section 4.5? Because as a student, I am definitely feeling the urge to just do regular math.
Oh, absolutely. The textbook highlights 2 major errors beginners make precisely because their brains are fighting the new rules. The first is using illegal symbols.
Illegal symbols, like letters.
Well, no, like digits that don't belong. For example, someone might write an answer of, say, 28 in base 5, but base 5 only uses the digits 0 through 4.
Oh, got it. So an 8 literally doesn't exist in that universe. Writing an 8 in base 5 is like, I don't know, trying to use a letter that isn't in the alphabet.
That is a perfect way to put it.
So what is the second error then?
The second is blindly applying base 10 facts to other bases, like trying to calculate 6 times 9 in base 17.
And just writing down 54 because that works in base 10.
Exactly. You might be using valid numbers for base 17, but the underlying math is completely broken. That rule simply does not apply there.
It's totally like trying to speak a new language, but stubbornly using English grammar rules. You might be using the right vocabulary, but you completely break the system.
Yes, which is why this exercise is so valuable for you. Working outside base 10 forces you to actually understand the mechanics of math.
Rather than just coasting on autopilot.
Exactly. You can't just regurgitate, memorize times tables. You have to construct the logic from the ground up based on the constraints of whatever system you're working in.
So what does this all mean? We started by talking about stripping away the comfort of our base 10 system to see the gears turning underneath. But the textbook poses a really fun question at the end. Which base is actually the most efficient?
Right, because you could technically use any base.
Exactly. Take base 2, binary. It only has 4 tiny multiplication rules.
Yeah, 0 times 0, 0 times 1 times 0, and 1 times 1. I mean, that is the entire multiplication table.
Which leaves you with a wild thought to chew on. If humans had evolved to calculate entirely in binary-like computers, would math be incredibly easy for us because there are basically no times tables to memorize?
Oh, wow. Right.
Or would those massively long strings of ones and zeros make it completely impossible for our human brains to process? It really makes you wonder if we traded the pure simplicity of binary for the familiar comfort of base 10.